Hi, I'm Jenny with KU Tech Transfer. I'm here to tell you about a cutting-edge morphing technology called Pressure Adaptive Honeycomb. Honeycomb uses pressurized, hexagonally shaped cells to create an internal framework that lets structures, like the wings of a jet, morph, depending on external or internal air pressure.
Really, the first inspiration for Pressure Adaptive Honeycomb comes from Mother Nature. If you ever look at a bird's wing, it's not a monolith, it doesn't stay put. Basically what a bird does on takeoff and often in landing, when it's flying really, really slow, the bird's wing has to curve quite a bit, and that curvature is called camber. And when a bird's wing is cambered, it generates a high amount of lift for the airspeed that it's going. As the bird flies faster and faster, that high level of camber is no longer needed. It's actually fairly draggy, and so the bird wing sort of sweeps back a little bit and it flattens out. We wanted to make an aircraft structure that would, in essence, emulate what Mother Nature has done.
Although other researchers have set their sights upon this lofty goal, each of the alternative morphing technologies has serious drawbacks.
Pressure Adaptive Honeycomb is distinctly different than some of the other adaptive structures. The problem that these other types of actuators have is that they are not certifiable by the FAA. It may take a decade or two to try and do that, and the cost would be prohibitive.
To this end, Dr. Barrett and his associates focused their research on creating an adaptive structure that's made from conventional materials, is easy to certify, cheap to manufacture, and that's morphing properties vary according to regular, predictable environmental changes.
Pressure Adaptive Honeycomb could be most easily integrated into the wings of smaller aircraft to droop the nose or to induce camber into the trailing edge. When that is done, the lift coefficient capability increases greatly. So aircraft like light sport aircraft or acrobatic aircraft would be enhanced tremendously. Another category of aircraft that may perhaps benefit the most is business jets. And business jets in and of themselves currently use some fairly rudimentary type of high lift mechanisms. If Pressure Adaptive Honeycomb, the direct operating cost of the aircraft would be reduced about 3%. If you can show that your aircraft has 3% less fuel burn than a competing aircraft, guess what? You're going to take market share. That is the fundamental advantage of Pressure Adaptive Honeycomb, is it makes your aircraft better.
Honeycomb's applications aren't limited to airplane wings, though. As you will see, Honeycomb's unique morphing properties promise profound applications for a wide variety of aerostructures, ground vehicles, and even wind turbines.
There are a number of other uses of Pressure Adaptive Honeycomb, in particular in naval architecture and automotive type environments, and some industrial applications too. So all the way from the sailplanes of undersea vessels or the rudders on ships. In the automotive world, spoilers can be manipulated with Pressure Adaptive Honeycomb. In terms of industrial applications, things like ceiling fans or industrial air movers can be made more efficient. One of the other applications of Pressure Adaptive Honeycomb is in wind turbines. Currently, wind turbine designers are forced into a compromise that is not optimum for low speed, it's not optimum for high speed, and only has a very, very narrow band in the middle where it is good. Pressure Adaptive Honeycomb can optimize the performance of the wind turbine for both low speed and high speed. All of these different types of applications would be enabled by this new type of adaptive material.